Hello everyone and welcome to this digital image processing of remote sensing data course, and in this 8th lecture we will be discussing a very important technique which is geo-referencing. Sometimes people also call it as image rectification, another thing. This is a common technique between remote sensing, that means in digital image processing, and GIS, and a very important one. The purpose basically of this geo-referencing technique is to transform your image from geometric domain to geographic domain. Why it is required? Because we know when image is acquired by a satellite sensor, then it belongs to, at that moment it belongs to the geometric domain, and then it doesn't carry the geographic coordinates like latitude, longitude. So in order to fit with other data sets, other maps and other things, especially in on a GIS or image processing platforms, then you require geo-referencing. That means transforming from geometric domain to geographic domain. One other important thing which we'll be discussing in detail about the origin of an image. The origin of image, that is the first pixel, it is defined at top left corner. So the first pixel is having first row and first pixel, and which we start counting from top left corner. Whereas in case of geo-reference image, it is the bottom left. So this also is very important to understand, because when we go for this geo-referencing, that also is incorporated while transformation is being performed. So geo-referencing, as you can see in the definition, is that transforms images or maps. Even maps can also be geo-referenced. If suppose I have scanned a Survey of India topo sheet. Now topo sheet might be having in print form the latitude, longitude marked, but this is an image, a raster image, and it is having origin at the top left corner. That means it is still in the geometric domain. So now this image, though it says image of a map, so we can call as a map, but that is also not geo-reference. So in order to bring these geographic coordinates and image, this technique is required to transform from geometric domain to geographic domain. So the geo-referencing basically transforms images, maps from geometric coordinate system to geographic coordinate system. And this concept, the entire thing, as you know, in digital image processing and also in the geographic information systems, it is based on the mathematics which we have gone through in our early days, is a coordinate geometry. So the concepts are really coming from coordinate geometry here, and that is why it is geometric coordinate system to geographic coordinate system using base map or having image having geographic coordinates. You need something standard on which you will transform, and so you require maybe some base map, maybe ground control points which are collected in the field using GPS or differential GPS, or maybe having a master image which is already geo-referenced. So taking that one as a master image and raw image which is in the geometric domain can be transformed by collecting the GCPs or ground control points, which we will see little later. Now before that we also understand very basic things about these latitude and longitude, that the most comprehensive and powerful method of geo-referencing, in which these are in bolts. This provides potential for very fine spatial resolution. So all kinds of spatial resolution images can be geo-referenced. There is no the geo-referencing is not dependent on a spatial resolution, allows distance to be computed between pairs of locations once it is geo-referenced. So you get in real distances like meters rather than in pixel values, and also supports other forms of spatial analysis, area measurement, length measurement, angle measurement. All it becomes very possible, and the values will be in the meters or in degree and so on and so forth. And the uses of well-defined and fixed reference frame which we use for geo-referencing, and which is based on the earth rotation and the center of mass and the Greenwich meridian or Greenwich Mean Time, because from where the 0-degree longitude passes. That is basically our reference point. So latitude, as we know, so quickly I will go through, is a angular distance in degrees, minutes and seconds of a point north or south of the equator, and lines of latitude are often referred as a parallels. And in case of longitude, is a angular distance again, both are angular distance, both are measured in degrees, minutes and seconds of a point east or west of the prime or that Greenwich meridian, and lines of longitude are often referred as the meridians. So here in this figure you can see that the latitude are shown the horizontal lines and the equator is in the between the earth. These are all imaginary lines except the 0-degree longitude, which has been marked on this observatory and in Greenwich near London. So that is the world reference point, or be also called prime meridian. So this prime meridian is shown over here, and which is a 0-degree longitude. So half of the globe will fall on the east of prime meridian and half of the globe on the west of prime meridian. Why these are important? Because in georeferencing, this is the basis to transform from geometric domain to geographic domain. Now, as you know that if it is a point is located here, then because of this angle, we will have a latitude as well and a longitude as well. Prime meridian is shown here. This is the equatorial axis or plane area is there, which is equatorial reference plane, and you are having North Pole and South Pole here. So any point on the globe can be defined using these longitude and latitude values, because both are values in angles. That is why we measure them or put them with degree, minutes and seconds. So now, as I have earlier mentioned very briefly, that when an image is acquired by a sensor on board of a satellite, the resulting image may have certain systematic and non-systematic geometric errors. One error is already coming because the most of the images which we use in digital image processing are coming from polar orbiting or near polar orbiting satellites, and due to the earth rotation, the skewness effects will always be present in raw images. So that also comes that through the sensor distortions, sensors may introduce some distortions. The scan skewness is always there because of rotation of the earth at the time when the data is being acquired, so that it is always skewed, and panoramic distributions might be there because it is covering a, depending on the spatial resolution, it may be covering a large part of the earth. So earth's curvature also plays very major role there to bring distortions in your image, and attitude of the platform, because these spacecrafts are moving in space. So there might be sometimes, because of some malfunctioning or other things during the data acquisition, there may be a change in velocity, there may be change in altitude, that means the height of the satellite is changing. There may be a pitch or roll or yaw movements. All kinds of these movements can also happen, because these are, they do not have, though we say in a fixed orbit, but really they are a free flying kind of thing. So they may have distortions like this pitch, roll and yaw, and all these movements of a sensor will bring distortions in your image, and our aim is to remove all of these in one go using this georeferencing technique. So that is why it is very, very important. Now some distortions may come from cross-track scanners. We have discussed different types of scanner, along track scanner, cross-track scanner and other thing. So cross-track scanners may bring distortions, especially in the images which are relatively having poor resolution. So like Landsat, MSS and others had this problem. When the scanners which are having the mirrors and post-bloom scanners or kind of, when they are having the mirror which moves, so these are the optomechanical devices, and then therefore there might be a change in the variation and the velocity, and that may bring a change in this. So like here the normal velocity should have been like this, but actual one is like this of a moving of mirror. The skewness will bring this kind of error in your image, so it is distorted because of earth movement when data is being acquired. There are some other errors which I have mentioned, like earth rotation error is skew, that is distortions coming from tracking data, that is earth rotation, due to earth rotation at the time of data acquisition, especially in case of polar orbiting satellites. Altitude variation, when suddenly there is a change in the altitude of the spacecraft, you may have variation something like this. You may have a pitch variation that suddenly dips towards the direction in which it is going, or in the opposite direction. So that may bring the pitch variation. The spacecraft velocity variation may bring a different kind of representation of the image. A roll variation, that a spacecraft is going and it rolls something like this and it tilts on the sides, so that we call as roll variation. And the another type of variation which can be introduced, or distortion in the image, of the yaw variation. So this yaw variation can also happen, and it is not that only one distortions will be there. There might be multiple distortions in a single image might be present. So many of such distortions can be removed by employing geo-referencing technique. So images, as you know, are stored as a raster, a two-dimensional grid. Each cell is representing a pixel value, which may be a reflective or emissive value, and then in this image they are stored in raw image as rows and column numbers, and hence are in geometric coordinate system. Our aim is to bring geographic coordinates with the image. So in order to display and analyze images with other georeference maps, data sets, we want to stack many images together of the same area, maybe image and map and some other like contour lines or some other features, or a geological map or a soil map. Then how you would do it, how you would achieve. If you are having a georeference maps, everything is georeference, then you can stack one on over other. So it is necessary to establish an image to word transformation. The purpose here is to transform from geometric domain to geographic domain. That converts the image coordinates to the real world coordinates. And real world coordinates are in terms of latitude, longitude, depending on which projection if you are using. If you are using like UTM, universal transverse Mercator projection, then these might be in your meters or in easting and northing, and depending on the different projection. But these all will be in a geographic domain rather than in geometric domain. So this is a common method, important method, which is also called image georeferencing, which we are using. Also somewhere in the literature you will find geometric correction, image registration, or image rectification. So many terms are used for the same processing, and is a statistical, what exactly it will do. So it is a statistical find, a polynomial of a given order. We will decide, depending on the distortions which are present in image, which polynomial order will be used. Polynomial equations we have studied in our school days. These are now going to be used, and of a given order depending on the distortion, that minimizes the errors in a transformation from the original image coordinates to a rectified image coordinates. So it's because not only it has to be transformed, but it has to fit in the new system, that is the geographic coordinate system. So this transformation is found by performing a least square fit for the coefficient of a given polynomial using ground control points, or in short we call as GCPs, that are picked by the users, and we decide that which is going to be the GCP. So what basically GCP is a ground control point, but the meaning here is basically that these points are common, are present in my master image or master map as well as in the raw image. For example, there may be two road crossings, or maybe a bridge over road, or maybe a bridge over the railway line. These are the fixed point, non-moving point. Whereas the bend in a river in a plain area cannot be the GCP, because in few years time that may move. So the age or the date on that the master image was acquired or map was made, and the image which is not yet georeferenced may have a different dates, and therefore such objects which are moving in character or in nature cannot be used. So we have to select very carefully the GCPs which are fixed. And the example I have given, the bridges, crossings, maybe aqueduct, and so on. So these can become our reliable GCPs, because GCPs plays very important role during the image rectification process. Here is a very schematic schematically the example of georeferencing is shown in a very simple fashion, that this is my raw image or input image which is not yet georeferenced. So it belongs to a geometric domain. Control points, 4 control points are shown. The corresponding control points in my master image or a map are also shown here, which is in geographic domain. Now what basically I have to find a polynomial equation, and the coefficient will allow me to shift pixel by pixel from this image, input image, to the master grid, which is a georeference one. And by doing a third step here, by this resampling, sometimes you may find people use word interpolation, but interpolation is not appropriate term here. Resampling is more appropriate term, and ultimately you reach to this. So there are 3 steps, major steps in georeferencing. First, tagging or controlling through ground control points, then tying your the image, the raw image with the master image or master map using these ground control points. The second one is finding the transformation coefficient, where each pixel will be transformed into a new geographic domain. And the third one is what is going to be the value of pixel which will be transferred, because it is not all the time. There are out of 3 major resampling techniques. The first one will transfer the original pixel value, but the other 2 will not transfer. So what should be the pixel value, how it would be decided, that will all be considered under the resampling. So there are 3 steps. First is the tying up, that is the using control points. Second one is finding the transformation function of a given order, which we will decide depending on the distortions which are present in the image. And third is what is going to be the pixel value, that is through resampling. Now how to decide about the polynomial equation of given order. So what order I will choose? If it is a simple transformation from geometric domain to geographic domain, that there is no other, that means there is no rotation, no change in scale, or no warping is required. It is a simple transformation from one domain to another, then we call as a first order polynomial. And also in literature you may find a conformal transformation function. When your image requires not only transformation from geometric domain to geographic domain 1, it also requires change in scale and also rotation of the image, then we will go for second order polynomial, or it is also called affine transformation. Third order polynomial is that when all these things which I have covered in second order, that means transformation from geometric to geographic 1, rotation of the image, change of scale, plus warping. And this requires, in case of relatively low spatial resolution data which are representing a curved part of the earth, and we want the flattened, because the georeference image will always represent the earth, even if a curved part of the earth, in a flat form. So that is why then in such cases you would go for third order polynomial. There are softwares you may find they have implemented up to 12th order, but generally beyond 3rd order is not required, because then all kinds of distortions will be handled by the 3rd order polynomial transformation. So why to go for higher order? Because once we go for higher orders, then the number of GCPs required will increase tremendously. So that has to be also kept in mind, and collecting GCPs is not a very easy task, because finding a reliable GCP is very, very important. How the ground control points, number of ground control points depending on the polynomial order will be required, that is decided by a this simple equation, that p plus 1 multiplied by p plus 2 divided by 2, and that means that if I go for just first order polynomial transformation, then I require minimum number of GCPs are 3. If I go for second order, then I require 6, and if I go for third order, then I require 10. Now one thing one has to remember these are the number of minimum GCPs which are required. Without these numbers, you will not have that option to go for transformation function. So these are the minimum, but in practice one should go by multiplying by 2. So if you are going for third order polynomial, then one should collect at least 30 ground control points. Some points, ground control points, which may be giving errors, large errors may be dropped, then may be recollected, and this through this iteration process, one can improve the georeferencing. Our aim to achieve within pixel georeferencing. That means that of course pixel is a unit, so it is indivisible. So beyond that we cannot perform. But our aim is that the error which we will get through this polynomial transformation coefficient calculation, that should be within the dimensions of a pixel. It will depend on the resolution. Higher the resolution, you will have a very small value to manage and to achieve, whereas lower spatial resolution, then larger values can be accepted. So this is very important, that though a minimum number of required depending on polynomial order are very small, but in practice multiply by 2 would give you much better results. So now like for example, suppose here 5 ground control points have been selected, and these have been chosen in this example, and the corresponding points of master image are also chosen, and this will give you that how much the differences are there, because this is in geometric domain, this is in geographic domain. Now if error is large, you may get a situation something like this. The point supposed to be here, the green plus sign, but whereas point is being displayed here. I have chosen a cross, but it is showing that if I go for now next step, then this point is going to be at the location which is yellow one. So the example shows from a control point, a yellow cross placed on the vector target data at a street crossing, which is this one, and the associated control point, that is the green cross, placed on the data, raster data, and the associated link, this blue line is represented by the blue line joining the control point. So this should not be very large. This is always displayed. If we zoom it little bit, we will be able to see it, what is the length. So this length should be very less in order to achieve a high georeferencing. Once the transformation is found, it is applied for every pixel in the input image, and the other operations to perform when doing a transformation of this type is to determining the pixel value. That is the third step, that is the resampling. Different types of resamplings are there, which we will see little later, and this is accomplished through using resampling techniques, that is nearest neighbor, bilinear and cubic convolution. The details we will see little later. So the transformation can be represented by a polynomial order M, such as this is a general equation for a given polynomial order. We can, depending on the requirement, as mentioned earlier, that if I am using a relatively low spatial resolution image, then it will be also representing a curved part of the earth. So therefore, the third order polynomial is most suited. But if it is having a relatively low spatial resolution data, then second order polynomial can also be chosen. Like an example I am taking from a very popular GIS software, maybe the same in ADAS image processing software, that in ArcGIS the image to word transformation is a 6 parameter affine transformation, that is the second order polynomial equation in the form of x1 ax plus b by plus c and y1 is equal to dx e by and f. The main aim, as I have been mentioning, that from raw image each pixel has to be transformed. Where it will go, this is decided by these equations. X and Y has to be decided. Initially X, Y's are in row number and column number. Later on these X, Y's becomes geographic coordinates. So where this pixel will go, that has to be decided through these equations. Now here this is the image space is given here. This is my raw image also, and this is the image which is having geographic coordinates. So that I transform pixel by pixel from here to here using that again the second order polynomial function. Here where this x1 or x dash should have been the calculated x coordinate of the pixel on the map, and y dash is the calculated y coordinate of the pixel on the map, and the x is the x which is after this a is the column number of a pixel in the image, and y is the row number of the image which is the raw image. Now what we are trying to achieve, x and y of for the new image which will be the georeference image, and now this A is the scale dimension of the map units in direction, because now in second order polynomial equation not only is a simple transformation from geometric domain to geographic domain, but we are also going to change scale and rotate the image as well. So that is why scale change will be controlled or handled by this A, and B and D are the rotation terms which will be used to rotate your image, because a raw image may have the skewness effect or a distortion due to other inputs as we have discussed earlier. These all will play very important role, and the C and F parameters which are coming in this second order polynomials are the translation terms xy maps coordinates of the center of upper left pixel, because raw image the coordinates we always consider from top left corner. And then last one is the E, which is the negative of y scale dimension of a pixel of map units in x direction. This is now again, as I was mentioning, that in the raw image the xy are always counted from top left corner, whereas in the georeference image they are counted from the bottom left. So this negative in the by scale has to be incorporated. Now as I have just mentioned, that the by scale, that is the E, is negative because the origin of an image and a geographic coordinate system are different, and the origin of image is located in the upper left corner, whereas the origin of the map coordinate system is located on the lower left corner. Now once we go for this, then we get this root mean square error because of these GCPs which we tie up with the raw image and master image. So when the general formula is derived, that means this polynomial order has been decided, then the applied to the control points a measure of error, the residual error is returned, and the error is the difference between where the from the point ended up, as earlier I shown the example, the blue line, larger the blue line, more the error, smaller the blue line, depending the color, I am just giving the example, the color may be depending on different softwares, and this line should not be that the line between where from the point ended up as opposed to the actual location that was specified to the point position. So this should be minimum as far as possible. If a ground control point is giving a large RMS error, then it should be deleted and maybe recollected, maybe at different location. A new GCPs may be collected, and by which we can reduce the overall root mean square of our registration process. So the total error is computed by taking the root mean square sum of all the residuals to compute the RMS error. So that will decide whether we are falling within 1 pixel when we go for a final step, that is the resampling or not. So this is important to see that we achieve within 1 pixel as the dimensions or the spatial resolution of the image. This value describes how consistent the transformation is between the different control points or the links like blue line. And when the error is particularly large, you can remove and add control points to adjust the error, which I have mentioned. Although the RMS error is good assessment of the transformation's accuracy, don't confuse a low RMS error with an accurate registration. For example, a transformation may still contain significant errors due to poorly entered control points. If control points are unreliable, though this RMS is low, that doesn't mean that you will achieve a good georeferencing. So one has to be very careful while collecting GCPs. GCPs have to be very, very reliable. Reliable means here the GCP which I am seeing in raw image should the same GCP, corresponding GCP, I should be seeing on my master image as well. Both should represent of the same age and same location, then I will achieve a very good georeferencing. And the more control points of equal quality used, the more accurately the polynomial can convert the input data to output point. As I have mentioned, the minimum say may be required 10 for third order polynomial, but it would be better to collect 30 or 20, so that you will achieve more points will allow you to drop few points. So if you have collected 30 instead of 20, though you are supposed to collect only 10, the minimum one, that at least you are having maneuverability to drop few points and still you will achieve a good georeferencing. So it is always in good practice to multiply by the 2 or 3 to achieve good. Now the third step or the final step in georeferencing is the resampling method. And here in this schematic, the master image is in the background and this rotated one is the raw image which is shown. Here in the form of matrix it is shown, but basically why matrix? Because we are handling raster data. So this is two-dimensional matrix. Now here the target is this one, which is the shaded one. If you see the overlapping here, that the pixel 1, pixel 2, pixel 3 and pixel 4. These are the just ID of pixel, not the real pixel value I am talking. So if in the first technique, that is a resampling technique, which is the nearest neighbor, what would be done? That first the search would be made over this overlapping images, master over this raw image, and then will be decided that which pixel of raw image is having the large coverage over the master image. So in this particular example, the pixel 3 is occupying the maximum area of your target pixel, and that means in nearest neighbor resampling, whatever the value pixel 3 is having, say it is having 105, so the target pixel will also have 105. So the pixel which is having the maximum overlap, that value will be decided or transformed to the target pixel. But if we want to involve 1, 2, 3 and 4, because they two are overlapping to different proportions, then if we go for weighted average, that the one which is having the maximum overlap will carry more weightage while deciding the pixel value of the target pixel, then a weighted average will be taken and all 4 pixel values will be involved in calculation. Depending on their overlap, they will carry accordingly the weightage, and that a new pixel value will be decided based on weighted average, and this technique is called bilinear. 4 pixels are involved. But if we go for more smooth image, then instead of 4 pixels we can go for 4 by 4, that means 16 pixels, and it can involve now distance to the target pixel. So that distance can be assigned a weight, and accordingly the values can be calculated, and this kind of calculation during resampling is called a cubic convolution. So quickly we will see that the nearest neighbor resampling determines the pixel value from the closest pixel to the input coordinate specified and assign that value to the output value. So the one which is overlapping maximum, that value will carry in the target pixel. This method is considered the most efficient procedure because there is no alteration of the pixel value. Original pixel values are intact. Many times we choose this nearest neighbor because later on we may be using that georeference image for image classification, and therefore we don't want to lose the image quality. We don't want to alter the image or pixel values, and therefore this method in that way is very good and efficient. It doesn't take much time to achieve this kind of resampling because not much calculation is required. So nearest neighbor does not alter the pixel value, and this is desirable if subtle changes of image values need to be retained. That, as I have said, in case of classification or some other, we don't want to lose the image quality, we don't want to deteriorate the image, and therefore the nearest neighbor is the best suited in such cases. And this method, however, induces a small error into corrected image. The error may be the offset partially by up to the half pixel, because we are choosing only 1 pixel value, so there might be a little error. Uncorrected image may be jagged or blocky in appearance, and if there is much rotation or a scale change. In case of bilinear, now 4 pixels are involved. Bilinear resampling determines a weighted average of the 4 nearest pixels in the uncorrected image, and the closer the center point of the pixel, the greater contribution or weight it will have to the final DNO pixel value to be assigned to the corrected. So as I mentioned earlier, that the pixel of raw image which is overlapping the maximum will carry the maximum weightage while deciding the pixel value for target pixel. Now bilinear resampling generates a smooth appearing resample, because here now pixel values are being altered. The pixel values are altered in this process, resulting in a blurring or loss of image resolution. So if you don't want to compromise on the image quality, then don't choose bilinear, then nearest neighbor. In that way is very honest kind of resampling technique. This method requires 3 to 4 times the computation time as compared to nearest neighbor, because 4 pixels are involved, their weighted average has to be calculated. In case of nearest neighbor, not much calculation, just transformation from original to target one. And highly accurate registration will achieve more faithful pixel values if I have done the first 2 steps very accurately from the original uncorrected image. And the last one here is the cubic convolution. This is more sophisticated method which uses weighted average of the 16 surrounding pixels of uncorrected image to approximate the value or estimate the pixel value of the new pixel space in the corrected image. So now 16 are involved, therefore it is not that efficient as nearest neighbor or bilinear, and it is closer to the perfect sin x over x resampler than the nearest neighbor or bilinear sampling, and avoids the disjointed appearance of the nearest neighbor method, because their half pixel problem which we may observe in case of nearest neighbor resampling will evaporate completely here, because 16 pixels average weighted average is being counted here, and it provides a slightly sharper image than bilinear method, but it also corrupts the original pixel value. means it alters the pixel value. And this method is not recommended if classification, as I have already mentioned, is to follow as the new pixel values may be slightly different from the actual radiance values detected by the satellite sensor. So there are always trade-off. You achieve a very good georeferencing after even cubic convolution, but same time you are altering the pixel value. So if in your application you don't accept the alteration or deterioration of the quality of image, then don't go for bilinear or cubic convolution. In that case, nearest neighbor is much better. But if you are you want the very high quality of georeferencing, you in this process, if values are altered, it is not a problem for you, then you may go for cubic convolution. As obviously the computation time of this procedure is about 10 to 16 times greater than for the nearest neighbor method. Because 16 pixels are involved, their weighted average will be calculated. And this brings to the end of georeferencing technique. Thank you very much.